Hi everybody, and thank you for being here. The presentation we're going to perform is about complex analysis in public transportation. But before going further, I would like to introduce ourselves, our lab and our team. So I'm Herbert Guérard, I'm a statistician for the CENTAI, which stands for Centre de Traitement et d'Analyse de l'Information. This is the Thales Laboratory of Information Processing. And my colleague here is Julien Naour. He is also a statistician, and we have worked together on topics related to data processing for public transportation. So this is the plan of our presentation. Firstly, we will present our lab. Then we will remind you some concepts about smart cities. We will talk about our workflows and their architectures, giving some feedbacks about their components. And we'll finally proceed to a little demo if we have enough time. So firstly, I would like to bring some more details about our lab. We are based in Gennevilliers in the northwest of Paris, and our teams forms part of the Thales Communication and Security Advanced Studies. And our main research topics are focused on big data, big analytics, and visual analytics. We are a team of 15 engineers composed of data scientists and developers. But in the lab, we like sharing knowledge so that each data scientist is led to work on development tasks, and inversely, each developer tries to improve his statistical skills. So in fact, in Thales, we have a kind of motto which says that even if the world is complex, decisions don't have to be. And this is with this in mind that our lab was created 10 years ago in order to be able to propose to our clients varied solutions, enabling them to extract knowledge from their data and to ultimately convert this knowledge into decisions. So through our work, we would like to build decision platforms dedicated to mobility. And as we can see on this scheme, sources of mobility data are diverse. And from supervision to information systems, they are all generating a lot of data. And if in the past those systems have been conceived more or less independently, and if they were operating in isolation, today they have to be interconnected in order to work together in an optimized way. And we think that data is the language that will enable them to communicate with each other. So the challenge we are facing consists in gathering all this data in order to extract relevant information. And these pieces of information can then be used by us, but also by systems themselves to improve their overall operation. So this is likely the most important facet of the smart transportation concept. So in the context of our project, our goal was to offer operators and transportation authorities an interactive solution enabling them to better understand mobility dynamics and needs, and to have some reports about the delivered quality of service. And in order to achieve that, we have based our platforms on several connectors to mobility data, on the development of several processing algorithms, and finally on an interactive visual mining portal for the end user. So in order to build this platform, we have worked in collaboration with the Computer Science Lab of Pierre and Marie Curie University, located in Paris, which is specialized in machine learning and large graph mining. We were supplied with anonymized ticketing data from STIF, which is the Paris Area Authority of Transportation. And this ticketing data represented about 770 million transactions over 3 months. This is about 10 million travels per day in more than 60,000 different stations. And our development were guided by the stiff needs in understanding travel habits, station usage, and disruptions. So we have performed two kinds of statistical data processing. The first one was dedicated to the network usage characterizations, thanks to a clustering algorithm aiming at detecting several travelers' profiles and discovering some possibly hidden mobility needs. This unsupervised clustering, sometimes called mixed clustering, is based on the coupling of several K-means algorithm iterations followed by a hierarchical ascendant clustering. And consequently, it doesn't require an a priori statement about the actual number of clusters existing in the data. So this type of analysis can serve several purposes. First of all, it enables to make data a bit more intelligible by reducing the dimensionality. This is quite desirable when we are dealing with big data, and this can offer some good starting points to data exploration based on successive drill downs. In practice, these profiles can also be used to check if products delivered by operators are in concordance with users' mobility needs, since algorithms' outputted profiles are only based on real mobility facts. This also can turn out to be useful when it comes to adjusting pricing policies, for instance. So the second statistical analysis consisted in building a random forest model. We have adjusted a simple model for the prevision of stations frequentation. It takes into account the day of week, the hour of the day, and holidays. It presents the advantage to be quite robust and to allow for adding other exogenous data like weather conditions or network events. In practice, it can be useful to react in advance to problems which can occur on the transportation network. We have also used this model in order to find anomalies in terms of over and under frequentation by measuring the difference between predicted and real frequentation value and raising an alert when the difference exceeded a threshold. The remaining work is then to find some explanations on the origin of the event which has given rise to the alert. So this type of models can be useful to get the analyst towards what can be relevant in the data and consequently to help him in taking decisions. So now Julien is going to show you the software architecture making the implementation of these kinds of data storage and processing possible.
So knowing that we have this kind of data to handle that follows the 3V, so volume, velocity, and variety, we choose to implement an architectural pattern, the Lambda architecture. So I think you have seen already today the pattern, but I will introduce it again. So basically, the Lambda architecture is composed of 3 layers: the batch layer, the serving layer, and the speed layer. The batch layer is here for 2 tasks: to handle all the data in an immutable and abundantly way, just to have an historical data set that is mostly raw data, and also to compute batch view on this data. So basically, it will launch long processes on this historical data to enrich this data and aggregate this data. After that, all this enriched and aggregate data are put in the serving layer. So basically, the serving layer is a database, or mostly a database that indexed all this batch view of the data. And after that, there is here the web portal that query this serving layer. So basically, the serving layer is here to have a quick ad hoc queries on the aggregate data. But the problem is the time that takes all the processes. So for in our case, with transportation data, it could take 16 hours to compute all the aggregated view on our data. So to beat this latency inherent of the batch layer, we have to add a speed layer. So basically, the speed layer will see the same data as the batch layer, parse it, and compute speed view of the data, and increment the serving layer. So that after that, merging the batch view and the speed view, we will have a real-time view of the data. Okay? So what is there is several interests in this kind of architecture. So mostly one of the main interests is that we have all the historical data that are available. So knowing that we have several features that are available. For example, we are human fault tolerant. Basically, if there is a problem in one workflow, one algorithm, we didn't lose any data because we could re-implement this workflow and relaunch it on all the historical data. So we didn't lose any data. Another feature that is interesting is the possibility to add a new feature on the fly and have this new feature available on all the historical data also. And we use also the historical data to build models, like prediction models, and export it in the speed layer so we could have prediction in real time and also anomaly detection in real time. So we choose this architecture pattern and we choose some technologies. So basically, we choose Kafka to get all the data from the different data feeds and put them in the batch and the serving layer. Kafka is basically a scalable broker. For the batch and the speed layer, we choose Spark. So Spark is a big data processing framework, which come with an interesting environment. So there is several projects that we use during our development. We use mainly MLlib. MLlib is a machine learning algorithm libraries. So we use the random forest and the k-means of these libraries. We use also the Spark streaming project, sub-project, excuse me. So basically what we'll do Spark streaming is to take a stream of data, cut it in blocks, and use the Spark engine to process the block of data. So knowing that, we could use mostly the same code in the batch layer and in the speed layer. After that, all the enriched and aggregated data are put in Elasticsearch. So Elasticsearch is mostly a search on an index engine, that comes with several features that are interesting for us, notably aggregation on GeoSearch. And after that, there is Kibana, which is a visual portal that query Elasticsearch. So we have done a fork of Kibana to handle our needs. So we implement several visualization and several features like translation, etc. So we do a fork of Kibana and improve it a little bit. So all the software that we choose are scalable by design and are open source software. So to summary, the Lambda architecture is generic and adaptable to different kinds of data. So, for example, we use the same architecture in several projects, like cybersecurity and also social network mining. And it's really efficient. You could handle data from many sources. It's adaptable to workload. So if you have more volume or more user, you just have to add some server, and you could handle the new need. You could have on-the-fly additional functionalities, as I said before. And it only needs data feeds from the current architecture, and you don't really have to change it a lot. So now I will present you some good practices and feedbacks about Spark and Elasticsearch. Okay, so good practices. Firstly, one of the good practices is to have quickly a working workflow. The idea here is to have workflows that come from the data to the visualization, so you could see what you have done in your workflow. For example, just have a little aggregation on your data and a little visualization could be really interesting. So after that, you could iterate quickly with this visualization and with your clients to show them what you have done, and also with your algorithm. If you implement some algorithms like prediction algorithm or clustering algorithm, you could see what they have done and see if they are good or not. So it's really good to have a working workflow quickly to iterate after that. Another good practice is to take a lot of time at the beginning to explore your data, to manage it, to have a good data set that you know really well and handle some missing value, for example, or some problems like that. So it's, like they say, 80% of the job of a data scientist, but it's really important. You have to take your time to do that, to gain time after. Another good practice is to do sample. So here we have a lot of data. It could take tens of minutes or even hours to process all of the workflow. So have just a good sample of your data could enable you to really explore your data and build your workflow on this sample really quickly. So it's really interesting to have sample of data. But you have to be careful with the scaling part, because if you build a workflow quickly with bad coding on your sample, it's possible that it could not handle the scaling part. And at last, the more metrics, the better. It's really interesting to have metrics for everything. Metrics about your cluster, metrics about the processing, metrics about data, metrics about statistical performance. It's really interesting to have that, because when you see a problem, you could see your metrics and find the origin of the problem more easily. Okay? So some feedback about Spark and Elasticsearch. So as I said before, Spark is a big data processing framework that comes with a lot of sub-projects. So there is some good parts with Spark. For example, it comes with a really nice API. So for example, there is broadcast, there is accumulators that are really good. Now there is a data frame API. So it's really interesting to use this project to explore your data and build a framework. The shell is really good. So Spark comes with a shell for the Scala and Python API. So it's really interesting, particularly for data scientists. Data scientists use the tools like IPython and R, for example. So using this shell, they are not lost. And behind the scene, all the algorithms that they build are launched on a cluster of gigabytes or terabytes of data. And it's really interesting for them to really explore all this data using the shell. So there is also some drawbacks with Spark. So Spark is still young. There is small bugs here and there, and so you'll always wait for the next version to have the new features that are available, new new connectors or etc. or some bug fix. So for me, Spark is still young, and it's little frustrating to always wait for the next version. The cache part could be tricky also, particularly if all your data doesn't fit in memory. So you have to really understand the API, use persist instead of cache, and so you have to be careful about that. And the ugly part in Spark is really the debugging part, particularly when you launch all your processes on a cluster. So, for example, during our project, we have done a group by key when a group by key, and in fact there were some key with several millions of events. So building on all our workflow on the sample, we didn't have seen that, but during the scaling part, there were this kind of problem that arise on that made Java space everywhere on the cluster. So it could be really long to find the origin of the problem just using the logs that are available in Spark. So it's really a main drawback in Spark for us. So about Elasticsearch. So there is also some pros in Elasticsearch. So it comes also with a good environment. There is several good projects in it. So for example, there is Marvel for monitoring and managing a cluster. There is Kibana for dashboard on visualization on your data. There is also Logstash for log management, etc. So Elasticsearch comes with a really good environment. You could leverage data quickly using this environment. And at the beginning, Elasticsearch could be really easy to use. In like an hour or two, you could have an Elasticsearch server up and running. You could also index data in it. You could query it. You could launch Kibana on it, like in 2 hours. And you could have some results on your data really quickly. So it's really interesting to do some proof of concept using Elasticsearch. So there is also some bad part in Elasticsearch. So Elasticsearch comes with no security. There is a project that is called Shield that is built by the company behind Elasticsearch, but you have to pay for it. And you have also some good practice to handle the security in Elasticsearch, but basically Elasticsearch comes with no security. In our workflow, in fact, Elasticsearch is a bottleneck, particularly when we want to reindex all the datasets. It takes, as I said, like 16 hours to launch all the workflow, and it's like 11 hours just for the indexing part. So really, Elasticsearch is a bottleneck in our workflow. And the ugly part, so basically, at the beginning, it's really a cool project. You could do many things, but after some days, you really have to master all the API, all the configuration to really do what you want with Elasticsearch. So it's like every other project, you have to really master the API to do what you want. So the conclusion, as I said before, we capitalized on this platform. We use it in cybersecurity and also in social network analysis. So it's really a good pattern of architecture. There is also a good integration between these projects. So for example, there is a Kafka API available for Spark streaming. There is also a project that is called Elasticsearch Hadoop to make the link between Spark and Elasticsearch. So there is a good integration between these projects. So you could have an open running workflow really quickly. So as I said also, Spark is still young. it's really hard to debug, and it could be a little bit frustrating. And what's next with this particular project? So we want to integrate other workflows. So we have other workflows that are just on paper for the moment, like simulation. What happens when you add a station in your network, and when you delete a station in your network. And we want also to improve our algorithm through collaboration. So right now we just use some robustified classic algorithms such as random forest or k-means, but we want to improve that part. So now a little demo. So there is already a problem with the resolution. So this is what we have done with Kibana fork. So this is basically a web portal with several dashboards that are available, several tabs at the top here, to really explore the different analysis that we have done during the workflows. So basically, here it's just a VM with just a sample of the data. It's not all the data. So I will show you firstly the atypicities part. So basically, here you have a timeline to do some filter on your data, and here you have a map to see all the atypicities that happen in your network. So for example, if I select bad selection. So if I select data here in the map, you have the Paris transportation network with the station here, and color scale to show if it's a big atypicity or not. So for example, here at the top we have an atypicity in red. So if you click on it, you have a graph that shows the prediction of our model, but also the observed data that happen in the network. So here we can see that the model is pretty good, but here we have some atypicity in the observed data. So in fact, we have done some research. So this is the Stade de France. So there were an event at that time, so that showed this strange behavior. You could also see other atypicities. So here you have also another atypicity. Sorry. So basically it's the same. The model is in red, and the observed data is in blue. And you have also a big atypicity here, and it's I think it's the Chinese New Year that happened in the south of Paris. So using this kind of tools, you could really find some interesting atypicity in your data. Okay, and I think I don't have much time. Putain. Sorry. So here is another visualization of the data. So at the left, you have some filters that are available about the data. So the mode of transportation, like subway, train, bus. You have the product, if it's for adult, student, etc. And you have also the typology, that is the clustering part, with some that is done during the clustering workflow. So basically, here this tab is for flow analysis. So the idea here is to select an area in Paris and find where the people come from. So they check out in this area and where they check in to go in this area. So if I select an area in the map, here, for example, I will have all the stations that are in this area, and also a little map about the check-ins. And if I select a station, I will see more precisely all the stations of the network and where are the big stations in the network. So here, for example, I think we see that most of the people comes from the center of Paris. Okay. So this is it with the demonstration. So thank you for your attention. Do you have any question? Yes.
How do you store the data? Because Elasticsearch can store the data, but now they claim that there are a search engine and indexation engine and should not put the data into Elasticsearch. But the database that just index the data into Elasticsearch.
Yeah. So, in fact, I'm not sure about the question. In fact, Elasticsearch is just here to index the batch view and the speed view of the data. All the data are stored in HDFS, and we just process batch view on on this data set, and then put them in Elasticsearch to index it and to query it using.
You index that in Elasticsearch data that are actually in HDFS.
Yes.
It's
Yes.
not clear on your
Okay.
data seems to be in Elasticsearch.
Yes, it's just the unreached and aggregated data that are in Elasticsearch.
But the result of your computation is in Elasticsearch.
Yes, exactly.
But you may lost. Actually, did say that because that not want to grant the capacity of the database and ensure that you will not lose your data. So
In fact,
eventually you may
it's not really.
result of your computation.
Okay. The question was.
The question is where are store the results of the computation, not the data, not the source data, but the result of all your computation.
So basically, all the results are stored in Elasticsearch, but if Elasticsearch fall, it's not really important because we just have to relaunch Elasticsearch, relaunch all our workflow to reindex all the aggregated view. So one of the main interests of this architecture is that all the data are immutable in the Hadoop environment, so that if there is problem after that, we could relaunch all of our workflow after.
So you maintain two clusters, HDFS cluster and an Elasticsearch cluster.
The question is, do we maintain two clusters?
Right.
So for the development part, we didn't have a lot of servers, so there was Hadoop and Elasticsearch on each server. But in production, you have to have two clusters here, like one particularly for Spark that have certain need in CPU and memory, and another for Elasticsearch that are mostly using RAM and SSD, for example. So yes, two clusters to maintain.
What are the changes that you made to Kibana that
So this is
are
mostly
you going to push them back to the community?
good question. So basically, what we have implemented in Kibana is some visualization that we need. So the heatmap part, I'm not. So basically, the visualization with all the station, it's our own implementation, and we have also implemented some feature like translation. I'm not sure that is available in Kibana, but I'm not. knowing Thales, we will not get them available for the community. And in fact, it's really specific development for our data, so I'm not sure that it could be really generic for other need. And this is mostly using leaflet for the implementation. So just with little search, you could find the same plugins that we used during to have the heat map.
When it comes down to the speed layer, usually it's kind of more real time, and you picked up Spark streaming here, and Spark streaming, well, you know, half a second sampling rate and stuff like that. So how are you dealing with that? Are you letting Kafka in the front of it deal with the throttling, or and because of the, I mean, we haven't had very good success with below, you know, 4 hertz or something like that, the Spark streaming down below. So what is that? Typically what we end up seeing down below is a storm or something like that, you know?
So in fact, we choose Spark streaming because we use Spark. So one of the main drawbacks of the Lambda architecture is that you have to implement the code 2 times, one for the speed layer, one for the batch layer. So it's the main drawback, and you could have some issue knowing that. So we choose to use Spark and Spark streaming so that we have just more or less more or less the same code in the speed layer and in the batch layer. So yes, we have some performance issue with Spark streaming, but for us, it's more important to have the same code in the two parts. Yes?
Hi. Would you consider swapping Elasticsearch for something if it has more problems in the future, or if it's just still a bottleneck or a bigger bottleneck in the future?
So right now, we are in the configuration part of Elasticsearch to improve the indexing part. So I think for the moment we are at 30,000 documents a second for the indexing in Elasticsearch. And we are still working on the configuration to improve that. So, and basically in production, it's more or less more incrementally, like you just compute the last day in the batch layer and just index the batch view of the day, not all the data set. I'm not sure that I'm clear here.
Yeah, yes, perfect.
Perfect, okay.
Thanks.
Other question? Okay, thank you.